Hey guys! Chemical equilibrium reactions are super important in chemistry. There's a forward reaction, where products come from the reactants. Then there's a reverse reaction, where the reactants are recreated from the products. Now, if you want to have either more products or more reactants, you can exert some kind of change on the reaction. In other words, you're changing the external conditions. Here you have three influencing factors. You can change the pressure, adjust the temperature, or change the concentrations of the substances involved. This is how you influence equilibrium. All this comes from the work of Henri Le Chatelier, and that's why it's called Le Chatelier's principle, or the equilibrium law. This is because equilibrium avoids disturbances or stress as much as possible. If pressure, temperature, or concentrations cause more stress on one side of the reaction than on the other, then the equilibrium falls back to the more chilled side. Let's have a look at the influencing factors in detail. We'll start with pressure, which is very important for gases. The best example here is ammonia synthesis. So nitrogen reacts with 3 times as much hydrogen to form 2 ammonia particles. What's important here is the number of gaseous particles on both sides of the reaction. On the left side of the reaction equation, you can see 4 gas particles and only 2 on the right. You can imagine that each particle takes up the same space. At the same time, the particles have the same space available. It's like on a train. On the reactant side, 4 particles of nitrogen squeeze into one compartment, and on the right side, there are only 2 ammonia particles. Now, pressure is increased. That means the train's getting smaller and there's less space available. This causes stress, especially on the left side. On the right side, there's a lot less stress. It's not so tight in the compartment. The equilibrium avoids the greatest disturbances or stress. In the example, it shifts to the right. This produces more ammonia, making the manufacturer happy. With an increase in pressure, equilibrium shifts to wherever each particle has more space for itself. So in reactions between gases, where there are fewer particles. With a reduction in pressure, the whole thing looks exactly the opposite. Now, each particle has a bit more space, the train compartment gets bigger. The particles now have more space than before. Now, it's not so tight on the left side anymore. That means there's not as much stress. So the particles there can relax again. Equilibrium shifts to the left. More reactants are produced. Equilibrium shifts to the side with more gas particles. For change in pressure, remember, a change in pressure only causes the reaction equilibrium to shift if you have different amounts of gas particles on the left and right side. But there are other ways to change the equilibrium. For example, by changing the temperature. Here, you've got a reaction of 2 nitrogen dioxide to dinitrogen tetroxide. This releases heat. Reactions where heat is released are also called exothermic reactions. The reverse reaction, on the other hand, consumes energy in the form of heat, for example. This is called an endothermic reaction. We also have a video on this. Okay, at a specific temperature, say 25 degrees Celsius, we're back at equilibrium. Okay, now let's raise the temperature. And there's some additional heat. For the exothermic reaction, heat is an additional stress. There's enough heat to get it going. When the temperature is raised, the endothermic reaction always gets a boost. So here's the one from right to left. The endothermic reaction can consume a significant amount of heat, making it stronger. Let's have a look at the opposite case. Now the temperature drops, so there's less energy. This means the endothermic reaction has stress, like the day before a chemistry exam. There isn't much heat energy left to allow the reaction to take place. Equilibrium avoids stress again. The exothermic reaction gets a boost and more nitrogen dioxide is produced. So far, so good. Now, there's one more way to change the reaction equilibrium, by changing the concentrations of the substances involved. In this example, the stress comes from the very high concentration of a reactant. This makes reaction that consumes this substance more intense. Here's an example. You want an extremely expensive substance to react with water to get the product. If you now add both reactants into the reaction 1-to-1, an equilibrium is achieved. Some of our product is formed, but due to the reverse reaction, a good bit of water, unfortunately, not much of the expensive substance reacted. That sucks, you paid a lot for it. But there's a solution. Does the law of mass action and the equilibrium constant still tell you something? In the law of mass action, the reactants are below in the denominator and the products above in the numerator. For our equation, it looks like this. The thing is, the equilibrium constant Kc is constant. It doesn't change. Now, if you increase the concentration of water, then the concentration of the product must also increase. Otherwise, Kc would change. But it's as stubborn as a mountain goat and stays right where it is. Okay, so if you dump the cheap water, this intensifies the forward reaction. This generates more product. Needless to say, it also goes the other way around. You can also try to keep a small concentration of the product by taking it out of the reaction quickly. You can also see this in the law of mass action. If the concentration of the product decreases, then the concentration of the reactants must also decrease. The equilibrium remains broken, forcing the reactants to be consumed more intensely, so there's not as many of them. At the same time, you have more and more products. Now almost 3 target circles and not just 1. In this way, you can also intensify the forward reaction. So remember, you have 3 options for changing chemical equilibrium. You can vary the pressure, temperature, or concentration of the substances involved. Here's another nice overview of it. Until then,